Hello, welcome back to Following Science, the podcast where we explore the intricate and fascinating world of scientific discovery. I'm your host, Rutu Parl, and today we're going to be diving into the brain to uncover the secrets of learning. Now, without further ado, let's dive right in. To start, let's lay the foundation by understanding what learning and memory actually are. Learning is the process of acquiring new information or skills, while memory is the ability to store and retrieve this information. These two processes are closely intertwined, and they form from the basis of our cognitive abilities. Now, imagine writing down notes in a class. As you take notes, you're engaging in the process of learning. Later, when you recall the notes for the test, that's your memory at work. But how does this happen on the neural level? To understand this, we need to explore the structure and function of neurons, the basic building blocks of the brain. Now, the brain is made up of approximately 86 billion neurons, each connecting to thousands of other neurons. These connections, known as synapses, are where learning and memory primarily occur. Now, when we learn something new, synaptic plasticity comes into play. This is the ability of synapses to strengthen or weaken over time in response to increases or decreases in their activity. Now, synaptic plasticity is crucial for learning and memory. Long-term potentiation, or LTP, is one of the primary mechanisms of synaptic plasticity. Now, LTP involves the strengthening of synapses based on recent patterns of activity, essentially making it easier for neurons to communicate with each other in the future. For example, if you're playing a musical instrument, the synapses involved in controlling the movements and remembering the notes become stronger as you play over time, making it easier to play over time. Now, conversely, there's long-term depression, or LTD, which weakens synapses. This is equally as important as it allows the brain to remove or downscale connections that are no longer needed, ensuring that the neural network remains efficient and adaptable. Now, of course, every time you want to bring something in, like remember some new information, some other information that's old, you might not need it anymore, needs to get out to make space for that new information. So it's like a cycle, so one is not better than the other, per se. Now, another key player in the neuroscience of learning is neurotransmitters. These chemical messengers transmit signals across synapses. Now, one of the most well-known neurotransmitters involved in learning and memory is glutamate. Glutamate activates receptors on the postsynaptic neuron, leading to a cascade of biochemical events that result in the strengthening of synapses. Now, there are several types of glutamate receptors, including NMDA receptors and AMPA receptors, and each play a crucial role in synaptic plasticity. Now, of course, there are also other neurotransmitters such as dopamine, which also play a significant role by modulating the reward and motivation system in the brain. Because when we receive positive feedback or rewards, dopamine is released, which makes us more likely to repeat the behavior that led to the reward in the first place. This is why reinforcement learning, where behaviors are encouraged or discouraged through rewards and punishments, is so effective. For instance, if you get a high score on the test after studying diligently, then dopamine release reinforces the behavior you're studying. But say in the same example, if you get a low score while you studied so much, then you stop studying in the future. Now, of course, learning isn't a one-size-fits-all process. There are various types of learning, and different people like different types of learning, and that's okay. Now, of course, all of these types of learning have different neural mechanisms, so let's explore a few. Starting with classical conditioning. This form of learning, famously demonstrated by Pavlov's dogs, involves associating a neutral stimulus with a significant one. Over time, the neutral stimulus alone can elicit the same response as the significant stimulus, because they both are paired together so much that the person who is trying to learn ends up associating the neutral stimulus with the result of the learning and forgets about the significant stimulus, kind of. Now, in the brain, classical conditioning involves changes in the strength of synapses between neurons that represent the conditioned and unconditioned stimuli. For example, if a bell rings every time a dog is fed, eventually the dog will salivate at the sound of the bell itself, thinking that it's about to get fed. because the neural pathways that link the bell to the food have been strengthened. Now let's talk about operant conditioning. Unlike classical conditioning, operant conditioning involves learning through rewards and punishments. B.F. Skinner demonstrated this with his famous Skinner box experiments, where rats learned to press a lever to receive food. This type of learning is heavily reliant on the neurotransmitter dopamine, as it reinforces the behavior that leads to the reward or the punishment in some cases. Now there's also observational learning. This type of learning occurs by watching others and imitating their actions. Mirror neurons, a specific type of neuron that fires both when we perform an action and when we observe someone else performing the same action, plays a crucial role in observational learning. Now, mirror neurons are fascinating because they allow us to learn and understand the actions and intentions of others. This neural mechanism is essential for social learning and empathy. For example, watching someone successfully solve a problem can help you learn how to solve a similar problem yourself, because that's your mirror neurons at work. Now, let's talk about a different aspect of learning: sleep, because sleep is a critical yet overlooked aspect of learning. Now, during sleep, especially during the deep and REM stages, the brain consolidates memories, transferring information from short-term to long-term storage. Now, of course, sleep is not just a passive state, it's a highly active time for the brain. The process of memory consolidation during sleep involves the reactivation of neural patterns associated with learning experiences. So it's effectively replaying the day's events and reinforcing synaptic connections. Now, studies have shown that people who get adequate sleep after learning new information are better able to retain the information compared to those that do not. That's exactly why before any huge test or a huge presentation, everybody tells you to get a good night's sleep, because oftentimes that can impact your performance on the next day. Another example is if you've spent the day learning new vocabulary in a foreign language. Your brain will replay these words during your sleep, and it will strengthen the neural conditions associated with them. This is why a good night's sleep is essential after a day of study, because it allows your brain to process and solidify the information you've learned. Now, as our understanding of the neuroscience of learning advances, new technologies and methods are emerging to enhance learning. Techniques such as neurofeedback, brain-computer interfaces, and even pharmacological interventions hold promise for the future. Now, let's talk about neurofeedback. Neurofeedback is where individuals learn to control brain activity through real-time feedback, and it's shown great potential in improving learning outcomes. For example, a student could use neurofeedback to enhance focus and reduce anxiety during studying, and it could potentially lead to better academic performance. Now let's talk about brain-computer interfaces, which enable direct communication between the brain and external devices. And this could revolutionize education by providing personalized learning experiences. Now imagine a classroom where each student has a brain-computer interface that adapts the material to their unique learning and style and pace. So every child can learn the way that's best fitted for them. And so they all can learn the same exact thing in the same exact way, and it can be more efficient. Now let's move on to pharmacological interventions, which are things such as drugs that enhance cognitive function. And this is a field that's also being explored. Of course, it's not something that's we just know a lot about, of course, because we're still exploring this. But what we do know about it is that the drugs in these interventions aim to boost neurotransmitter levels or improve synaptic plasticity, and it potentially enhances learning and memory. However, ethical conditions and potential side effects should be monitored when talking about these interventions, because these are drugs, and so it's important to use them wisely. Otherwise, some people might get hurt because we didn't take care of the side effects. Now, the neuroscience of learning is a vast and complex field, but understanding the basics can help us appreciate the incredible capabilities of our brain. From the strengthening of synapses to the role of neurotransmitters and the importance of sleep, each aspect provides a piece of the puzzle. Now, as research continues to evolve, we can look forward to new insights and innovations that will further unlock the potential of the human mind. Now, as I wrap up this episode, I just want to thank you all for joining me on this journey into the neuroscience of learning. If you enjoyed this episode and, of course, learned something, please subscribe and leave a review. Now, until then, keep learning and stay curious. This is your host, Rutu Rapal, signing off.